Everyone, welcome to Trig 101, and this is a little excursion into that branch of mathematics that plays such an important role in our everyday lives. If you look at the shapes of buildings, the shape of most objects, they're actually related to angles and triangles. Okay, so trig itself is really nothing more than trying to understand the relationship between the angles and the related triangles. So that will be our starting point. And as you probably come across the concept of a triangle, the three-sided figure. Well, in general, we have three types of triangles. The first one that you see in the picture right now is something called a scalene triangle. Do you remember the properties of a scalene triangle? Well, as indicated here, a scalene triangle has three different measures of side. So each of the sides are of different length, and each of the angles of different size. And you remember that we measure angles in degrees. Okay, so that goes for the scalene triangle. There are two other triangles. One is the isosceles triangle. And what is the fundamental property here? Well, there are two sides that are equal in length, and then the corresponding base angles, that's what I like to call them, are equal. So if you look at triangle ABC, we know that side AB is equal to side AC in length, and the corresponding base angles, denoted like this, are equal. Very, very important in the study of geometry as well as the study of trig. Okay, which is the most symmetric one, or highly symmetric, and that is called the equilateral triangle. For two reasons. One, all sides are equal in length, and having said that, each of the angles actually measures 60 degrees. So if you quickly look at that, and you don't have to be a rocket scientist, you know that the sum of the interior angles of a triangle would be 180 degrees. So 60 times 3 is indeed 180 degrees. All right. And then we have these very special triangles. And that class of triangle that we're looking at right now is called the right angle triangle. And it's going to play a very, very important part in our study of trig. So in the right angle triangle, you have at least one angle equal to 90 degrees. You cannot have two angles equal to 90 degrees. Why is that? And it's a unique triangle because there's a theorem based on this triangle. And you would recall the name Pythagoras and the Theorem of Pythagoras. Well, I've just got a little slide here showing you that the Theorem of Pythagoras, while it has many applications in mathematics, it has also many applications in architecture, in agriculture, and if you are like me who believe in aliens, we could, for instance, if we want to communicate with beings from outer space or other parts of the universe, we could use the Theorem of Pythagoras. In fact, we actually did to communicate or beam up signals using this theorem. I mean, if you look at the ancient pyramids, you'd find that the Theorem of Pythagoras is very evident in the construction of the pyramids. And if you visit the Louvre in Paris, then you notice that the composition of the structure is highly based on, obviously, mathematics, and in there it incorporates the Theorem of Pythagoras. So what is the Theorem of Pythagoras? It's very simple. It relates in a right angle triangle. It relates the measures of the sides, but not any measure of the sides, but the square of the sides. So this side, the longest side, is called the hypotenuse, not the hippopotamus. And the hypotenuse is always opposite to the 90-degree angle in that triangle. And what Pythagoras was able to show many, many, many years ago is that the square on the hypotenuse is equal to the sum of the squares of the other two sides. So if you're given the lengths C and B, if you square each of them and take the sum, you will get the hypotenuse, or the longest side, squared. This is what it means. The square on the hypotenuse. There's the hypotenuse here, because it's opposite the right angle. that square, the area of that square, it turns out to be 25, is equal to the sum of the areas on the other two sides. Now, did you know that? So 9 plus 16 equals 25. And there we have the Theorem of Pythagoras. Now, trig, and what is it? Well, if we confine our studies to right-angled triangles, we have an angle associated with this triangle. We're going to call this angle theta. There's a right angle over there, right? Associated with the angle theta is the opposite side to that angle. The side lying along theta we call the adjacent side, and of course the longest side being the hypotenuse opposite the right angle. So we're going to make use of this simple right angle triangle to introduce to you a series of what we call ratios, and we're going to give them names. And this is what you've learned. Firstly, in a right angle triangle, we know the theorem of Pythagoras will hold true. That is, a squared plus b squared is equal to the hypotenuse squared. That's pretty straightforward. That is well known. But I'm now going to introduce to you three very important trig ratios of the sides. So the first definition is sine theta, not sin but sine. Sine of theta is the ratio of the opposite side of the triangle divided by the hypotenuse. And normally the opposite side we will call y, the adjacent side we'll call x, and the hypotenuse is r. So sine theta is opposite y over r. Cos theta is the adjacent side, which in this case is x over r. And finally tan theta is opposite over adjacent. So this becomes y over x. Now you don't have to be a genius to realize, hey, hang on, there's something interesting happening over here. Y over r, x over r, y over x. R's gone. So it looks like tan theta is sine theta over cos theta. Let's just check that. Sine theta is y over r. Cos theta is x over r. So y over r, you got a fraction over a fraction times, you invert the second one, r over x. The r's cancel out. And for sure as God made little apples, look at that. It's y over x. And y over x is tan theta. So we've just proved a very neat little result. That tan theta is indeed sine theta over cos theta. Okay, so now that we've defined these trig ratios, we just need to have a look at how these ratios can be used in terms of determining the sides of triangles as well as the angles. So what we have to do is just agree on some convention. So if you look at your coordinate system here, there's your y-axis up there, that's your x-axis there, and we divide that obviously into 4 quadrants. The first quadrant, and this is basically moving in an anti-clockwise direction, is valid for the angle, say, greater than 0 degrees. Let's call the angle theta, less than 90 degrees. So if we're going in an anti-clockwise direction, that's basically what I mean from what I just wrote down there. In the second quadrant, theta is valid for angles greater than 90 degrees, but less than 180 degrees. So you're looking at the angles there. And what can you tell me about the third quadrant? Well, in the third quadrant, then theta should lie between 180 degrees and less than 270 degrees. So we're looking at that. And then finally, to complete that revolution, in the fourth quadrant, theta has to be greater than 270 degrees, less than 360 degrees. So if you had a look at how we divided these quadrants up into the angular portions as well, we are now speaking of positive angles. Positive angles. Right. So with positive angles, we basically move around in an anti-clockwise direction. So the next question we'll ask is, can we now work with negative angles, and what does that mean in terms of direction? And more importantly, what does it mean for trig ratios? Okay, so there are no prizes for guessing. When we look at negative angles, it's really nothing more than changing the direction. So in this case, we're going to be moving in a clockwise direction around these quadrants. And so if we start, we're actually looking at the fourth quadrant, and in terms of negative angles, we're looking at theta lying between 0 degrees and minus 90 degrees. The third quadrant, you'd have minus 90 degrees theta, and then if you move all the way around, it'll be minus 180 degrees. Second quadrant, minus 180, yes, you guessed right, theta less than minus 270 degrees. And the first quadrant is where we are now completing that revolution, so we expect it to be minus 270 degrees theta to minus 360 degrees. So this sort of convention is very, very important, especially in the applications in terms of physics and engineering as well, as you would see later on in your pursuit of these subjects. Okay, so we have the angles there, we've got them defined, and we're quite happy now to actually apply our various trig ratios and see the applications or the importance of these. Okay, so we all learned about the cast system. It's very, very important in actually remembering the behavior of these trig ratios, especially their signs in each of the quadrants. So why cast? Well, the first thing you notice here is that in quadrant 1, let's just start over there, all trig ratios are positive. In the second quadrant, it's only sine theta that's positive. Third quadrant, tan theta. And finally, in the fourth quadrant, cos theta is positive. And remember here, when I use the cast system in this sense, I'm talking about positive angles. Okay, so if you have a look and we're moving in an anti-clockwise direction, so cos theta, or in the first quadrant, sine theta in the second quadrant, and then finally tan theta in the third quadrant. Okay, now if we go back to the definition, so we remember that sine theta was the opposite side over the hypotenuse. So if I had to create a little triangle out here, let's leave the angle theta there, just like that. So that's my angle theta. Then the opposite side is nothing more than the side y, and the adjacent side is x, and let's call the hypotenuse r. So sine theta is opposite, which is y, and the hypotenuse is r. But y and r are both positive. So if y and r are both positive for this triangle in what we call standard position, it tells me that sine theta is positive. Let's look at cos theta. Cos theta is adjacent over hypotenuse. Adjacent side is x, which is a positive number in this sense here. The hypotenuse is positive, hence cos theta is positive. What about tan theta? Tan theta is opposite over adjacent. The opposite side is y, which is a positive number. The adjacent side is x, which is also positive, hence tan theta is positive. So there we've seen this quite easily, that all ratios in the first quadrant are positive. Now just for fun, if we take an angle theta, say in the second quadrant, in the second quadrant, we are looking at there, and the angle that we're concerned with would be this guy over there. Now, if I look at the y, which is the opposite side, I can think of just dropping a vertical there. That's the opposite. That's the adjacent. So let's take a very simple ratio like sine theta. Let's just see whether it is indeed positive. So in the second quadrant, sine theta here is opposite, which is y. The hypotenuse is a positive number, so that's r. So again, y is positive, r is positive. Positive number over positive number would be positive here. Let's look at cos theta. Right neatly. Cos theta is adjacent over hypotenuse. But the adjacent side, look at this. It's to the left of the origin. It has to be minus x. The hypotenuse is still positive, and hence cos theta would be negative in the second quadrant. So what I challenge you to do is work out tan theta. Okay, let's just have it. Look, it's so much fun here. Tan theta is opposite over adjacent. Opposite is y. Adjacent is minus x. So tan theta is negative in the second quadrant. So I challenge you as homework, out of curiosity, or you want to share this with your neighbors, is to look at the different ratios in quadrants 3 and 4 and convince yourself that tan theta is positive in the third quadrant and cos theta is positive in the fourth quadrant. Now I notice here's a little error. When I say tan theta, I didn't mean less than 0, and I think you would have known this is actually greater than 0. So that's not being that's being very naughty. So let's just change that to avoid the confusion. Excellent. So learn the car system, prove it for yourselves, going through each of the quadrants and each of the ratios. So it's not just remembering it for the exam or a little test, but remembering it for life. Okay, so here's typical test question or exam questions. Pretty standard. We're given a 0.54 in the first quadrant, and we have an angle theta as shown. And so what we want to do is actually now calculate the various trig ratios without the use of a calculator. So the first thing we want to do is complete that right angle triangle, and we notice that the opposite side, side opposite the angle theta, is the y value. The y value is actually plus 4. The adjacent side to the angle theta, the adjacent side, let's call that adjacent side, and that's going to give the x value, which is 5. If you think about this very carefully, we have a right angle triangle. We've got two sides. We need the hypotenuse. We use the Theorem of Pythagoras. And what does Pythagoras tell us? It tells us that the hypotenuse, if I want to call that h like this, so if we go h squared is equal to the opposite side squared, in this case, plus adjacent side squared. The opposite side was 4 squared plus 5 squared. That's 16 plus 25, which is 41. And so the hypotenuse is nothing more than root of 41. Let's just leave that in third form. Now, the next thing we want to do is write down the various ratios. So, for instance, if you look at sine theta is opposite over the hypotenuse. Opposite side was 4. Hypotenuse was root 41. Cos theta, what is that? Adjacent over hypotenuse. The adjacent side is 5. Hypotenuse root of 41. And tan theta, opposite over adjacent. So if we got opposite over adjacent, then we're going to go 4. The adjacent side is 5. So it's very, very simple to understand. And I remember from school days, many, many decades ago, the teacher kept wrapping on about SOHCAHTOA. Sounds nice. SOHCAHTOA. Sine, opposite of hypotenuse. Cos, adjacent of hypotenuse. Tan, opposite over adjacent. SOHCAHTOA. Don't forget that. It's very interesting. It's very exciting. My maths teachers, we're all excited about SOHCAHTOA. Okay, so here's something different from the first slide, except now we have a point in the second quadrant, minus 2, 5. So we're looking at a positive angle, theta, there. And you'll see straight away that the opposite side is 5. The adjacent side is minus 2. So we want to use old Pythagoras to get the hypotenuse squared. The opposite side, I said, was 5 squared. And the adjacent side was, now be careful, it's not minus 2, but it's minus 2 all squared. So that's 25 and 4. That gives you 29. So that becomes root of 29. And then we can practice SOHCAHTOA. Sine of theta is opposite of hypotenuse. The opposite side was 5. And the hypotenuse was root 29. Look at the cast system here. Sine theta is positive in the second quadrant, and we know this. Cos theta, adjacent of hypotenuse. Adjacent of hypotenuse would be minus 2 over root of 29, less than 0. And I want you to tell me what tan of theta is. Opposite is 5. Adjacent was minus 2, less than 0, as we expect. Sine is positive in the second quadrant. Cos and tan are both negative in the second quadrant. Pretty straightforward. All right, so just for fun, let's try to work with one theta being in the third quadrant. It's going to be now positive. If you have a look at the point, it's minus 2, minus 4. So the adjacent side, which is the x value, is minus 2, and the opposite side is minus 4. So we appeal to Pythagoras again to work out the hypotenuse. Squared is just the sum of the other two sides squared. So the opposite side squared was minus 4 squared plus minus 2 squared. Watch the use of brackets. So that's 16 plus 4. That gives me 20. So the hypotenuse is nothing more than root 20. So let's just find out what sine of theta is. It's opposite over hypotenuse. The opposite side was minus 4. The hypotenuse is root 20. And as expected, sine of theta in the third quadrant is negative. Cos theta is adjacent over hypotenuse. Adjacent here is minus 2. Hypotenuse always positive. Gives me a negative value at the end. And we know that tan theta is positive. Let's have a look and see. So that's opposite, which is minus 4 over minus 2, which is plus 2. And as expected, it's greater than 0. Can this get any easier? And you thought trig was difficult. No. Because we're having so much of fun, we just can't put our pens down. Let's look at one theta in the fourth quadrant. And the point here is 3 minus 2. So it tells me that the adjacent side is positive 3. The opposite side is minus 2. Pythagoras again. Write neatly. So the hypotenuse squared is just the sum of the other two sides squared. The opposite side was minus 2. Squared that, and then you got 3 squared. That's 9 and 4. That's 13. So the hypotenuse is root 13. You notice that, we got 8 squared, so we're taking the square root of 13. Should be plus or minus, but the hypotenuse is positive, always positive. So we've got root 13. So let's just test this. Sine of theta is opposite over hypotenuse. The opposite side we said was minus 2, and that as expected to be negative. Cos theta we know is positive, so let's just test that. Adjacent side is positive 3. Root 13 is positive. And look, there's no thinking here. SOHCAHTOA. Opposite side was minus 2, adjacent there. And as expected, tan theta in the fourth quadrant is negative. And we all excited. And up to this point, I think there's no great mystery in applying these trig ratios. So these type of questions are quite nice. I mean, they actually make you think up to a certain point. It says if 3 cos theta plus 2 equals to 0 and sine theta is positive, calculate tan of theta. Now, straight away, if you have a look here, it's interesting because they are telling you that sine theta is positive. Now, we've been through this over the last 15 minutes, and that is, in which quadrant is sine positive? All smoke, Texan cigarettes. So we know that sine theta is positive in the first quadrant, and sine theta is also positive in the second quadrant. So it tells me that my solution, or my angle theta, could either lie in the first quadrant or the second quadrant. Then we're given one more piece of information. 3 cos theta plus 2 equals to 0. So if you have a look at that, 3 cos theta plus 2 equals to 0. Can we not write that cos theta is minus 2 over 3? Haha. Now, cos theta is equal to minus 2 over 3 is less than 0. In which quadrant is cos theta negative? So we know that cos theta is negative in the second quadrant. It's also negative in the third quadrant. So which ones do we choose? Well, if you look at the question, we've got to satisfy both these conditions. 3 cos theta plus 2 equals to 0 and sine theta to be positive. So our solution, without thinking too much, has to be, or angle theta has to be in the second quadrant. So if cos theta is minus 2 over 3, let's just go back here. Cos theta is minus 2 over 3. Let's try and draw that. That means the adjacent side over the hypotenuse, and we've been saying this, and our heads are now actually paining, that the hypotenuse is always positive. The hypotenuse is going to be 3, so the adjacent side has to be minus 2. So basically, we've got minus 2 down here. We've got the hypotenuse, which is 3. The opposite side we don't know, and that's 90 degrees. So there's my angle theta there. How do we work out the opposite side? Again, Pythagoras. You know, we've got hypotenuse squared is equal to the sum of the other two sides squared. The hypotenuse was 3 squared. The other side, which in this case was the adjacent side, was minus 2 squared. So the opposite side would be 3 squared, which is 9, minus 4. So the opposite side is going to be, so 9 minus 4, watch this, and take the square root of that, is going to be plus or minus root 5. Interesting, we have two possibilities, plus or minus root 5. So we could have the opposite side having a value of plus 5, or if it was root 5, it will lie down here. But if we take theta to be in the third quadrant, then we violate what we're given, that 3 cos theta plus 2 equals 0 and sine theta greater than 0. So we've got to take the opposite side equal to plus root 5, and we discard the minus root 5. So please think about that very carefully. So now know that the opposite side is plus root 5. What is the question asking us to calculate? They're asking us to calculate tan of theta. So tan of theta is opposite over adjacent. The opposite side we've just worked out to be plus root 5, and the adjacent side we know is minus 2, and we expect this. Tan of theta is minus root 5 over 2, or root 5 over minus 2, or minus root 5 over 2. It is negative. Theta is in the second quadrant. I hope you understand this. Work through this problem very slowly. These are the fundamental building blocks of trig. Start slowly, understand the fundamentals before you get on to the bigger things. This is a beautiful question. It says, if sine theta equals to p and we're restricting theta, calculate cos squared theta in terms of p. I can tell you why most students don't like this. You'd prefer, instead of p, you'd like a number like 1 over 2 or 3/4. But how do you put p into your calculator? That's where most students are stunned. Well, p is just a number, so let's just go with the flow here. The fact that theta lies between 90 degrees and 180 degrees, it tells us that the angle theta, if you recall, I'm just going to do this slowly, that's 0 degrees. That would be 90, and this is 180 degrees. So if theta lies between 90 and 180 degrees, and surely the angle is in the second quadrant out there. And it says sine theta equals to p. Now have a look at that very carefully. Sine theta is equal to p. It's just not p, but p over 1. And that should be opposite over hypotenuse. So the opposite side is p. And the hypotenuse is equal to 1. So what it tells me is I need the adjacent side. How do I calculate that? Well, it's pretty straightforward. The adjacent side is given to us by Pythagoras. Yep. Hypotenuse squared is the sum of the squares of the other two sides. Opposite, we said, was p squared. Adjacent is what we're solving for, and the hypotenuse is 1 squared. So a squared is 1 minus p squared, which tells me that a must be plus or minus the square root of 1 minus p squared. Plus or minus, which means there are two possibilities for the adjacent side. But the fact that we've restricted theta to the second quadrant, we have to take the adjacent side to be minus the root of 1 minus p squared, because it's negative. It's to the left of the origin. So the adjacent side is negative. So they want cos squared theta. But before we get cos squared theta, let's get cos theta. It's adjacent over hypotenuse. We work that out to be, it's a beautiful question, over 1. So that's what cos theta is, which tells me straight away, finally, that cos squared theta, if I square both sides, is just 1 minus p squared. Such a sweet question with a beautiful answer. Brilliant. Love it. Ho, 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 ho. So here we've got something slightly more complicated. Again, if you look at this picture very carefully, I can see 3 triangles, a massive one over there, a little one which is a right angle triangle, and one that's not so right angle. So there's a right angle over there. So 2 right angle triangles in this picture, and we can give it some things to call this little a. You want to call that x, maybe call this side here y, call the hypotenuse of the big triangle r. Let's call that capital R, and of the small triangle little r. So in triangle ABC, this little blue triangle there, I want to let this angle be theta. So you work with me. What is sine theta equal to? What is cos theta equal to? What is tan theta equal to? So in here, the side opposite theta is going to be y, which is that guy. And the hypotenuse is of the small triangle, that's going to be r. If you get cos theta, the adjacent side is what I call a, the hypotenuse is r, and tan theta is opposite over a. Right. Let's go to triangle, the big right angle triangle, ABD. Interesting. Let's let this angle over here, let's give it a new letter instead of keep using theta. They are beautiful letters on the Greek alphabet. Let's call it alpha. You tell me, what is sine alpha equal to? Well, sine alpha is now there's alpha. The side opposite alpha is look at the big triangle, is y. And the hypotenuse is capital R. It's the big one over here. What is cos alpha equal to? Now here you've got to be very careful. Cos alpha is not CD. It's of the big triangle, so it'll be BD. So BD, let me write that down, over hypotenuse, which is R. But what is BD? BD is A plus X all over R. Now these are just numbers, okay? We just represent them as letters, but these are actually actual measurements if you're actually doing the trig. I've lost all my data. You could, for instance, remember now I have this side over here, and I have the hypotenuse of this triangle. So you'd say something like cos of x is the adjacent side. Let's call that side A over 12, right? But we had already known A. So if I know A, then I can work out X pretty straightforwardly. So please check that. So let's just label that again, A, B, C, D. Then it turns out that it's BD over 12, right? So if you know BD over 12, then you can work out cos of X. Pretty straightforward. So for instance, just let's assume that cos X is equals to a half. How do you solve for X? In your calculator, you press in 1 over 2, which is 0.5, inverse cos, or second function cos, to give you the angle X. All right. Special angles. Why are they special angles? Because they pop up everywhere in physics and in engineering, and sort of stuff that you need to master, you need to learn. Okay, so there are two triangles that are important here. They're both right angle triangles, but look at the angles. If you look at the first picture on your left, it's an isosceles triangle, right? So the base angles are 45, 45. And obviously each side measures 1, 1, and the hypotenuse √2. And you need to know these things. Like, for instance, someone's going to ask you, what is sine of 45 degrees? Now, it's not like you're going to draw the triangle and figure this. Sine of 45 is opposite of hypotenuse. Quickly, 1 over √2. What is cos of 45? 45 adjacent of hypotenuse, 1 over √2. What is tan of 45 degrees? It's 1 over 1, which is 1. You should know this better than your own name. Look at the triangle on your right. 30 degrees, 60 degrees. So for instance here, what is sine of 30 degrees? Sine of 30 is opposite of hypotenuse, which is 1 over 2. What is cos of 30 degrees? √3 upon 2. Just know this. Fire away. What is tan of 30 degrees? The tan is opposite over adjacent, 1 over √3. Let's go with 60. What is sine of 60 degrees? It's opposite over adjacent. Opposite over hypotenuse. Just checking whether you're following me. What is cos of 60 degrees? Cos of 60 here is adjacent over hypotenuse, 1 over 2. And finally, tan of 60 degrees, √3 upon 1. Now you'll notice something very interesting here. Okay, sine of 30 and cos of 60. I'm just going to circle them. Cos of 30, sine of 60. They equal. And they equal because these are what we call co-ratios, right? Sine of theta is related to cos of some theta. So we can conclude here, for instance, that sine of theta is equal to cos of 90 degrees minus theta. But you knew that, right? But please remember these special angles. Let's put a little picture here just to remind you how important these are. Okay, so just go through these, and if you do forget, then you must be in a position to actually draw these triangles very quickly, put in the measures of the side, and then pull out these angles very, very straightforwardly. So for instance, someone just asked you, what is tan of 60 degrees? Don't even look at the picture. Tan of 60 is root 3, which is the opposite side over the adjacent side, which is root 3, like this. Very, 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 very important. Now, here's the big one, trig identities. And in the exams, you're always asked to prove these identities. Well, I'm not sure whether you've come across things like sine theta is 1 over cosec theta, cos theta is 1 over sec theta, tan theta is 1 over cot theta. Generally in school, we focus on sine, cos, and tan. But what's important here would be these ones. Tan theta, we've already proved, is sine theta over cos theta. But these identities that you see at the bottom, absolutely important. Cos squared plus sine squared, or sine squared plus cos squared equals to 1. I'd like to focus on the word identity. An identity is a relationship which is true for all values, in this case of theta. It's different from an equation. You see, if I had an equation like x minus 1 equal to 0, this is only true if x is 1. But an identity is true for all x. So we have 3 here, 1, 2, 3, and I'd like to prove the first one. So I need to prove that sine squared theta plus cos squared theta equals to 1. The proof is very simple. We got to go back to that right angle triangle that we had. Call that angle theta. That's 90 degrees. And what I want to do is I'm going to call this triangle A, B, C. The side opposite C I'm going to call little c. Side opposite A I'm going to call little a. Sorry, opposite angle A, and then B is there. So in this triangle, in triangle A, B, C, you can see that sine theta is opposite over hypotenuse. Okay, and cos theta is adjacent over hypotenuse. Now, what does it mean? We've got to square this because we're going to prove sine squared plus cos squared equals to 1. So let's take sine squared theta plus cos squared theta. What is that equal to? It's b squared over c squared plus a squared over c squared. That doesn't look like it's 1. But its common denominator is c squared. So what I have on the top is b squared plus a squared over c squared. But you look at this and you say, wow, this is amazing. Because b squared plus a squared is c squared. How do we know that? Theorem of Pythagoras. So that is equal to 1, and it completes the proof. Amazing. All right. So I was just going to say, if I draw that very quickly, just to remind you if we went too fast there. So this was A, this was B, this was C, we call that C, we call that B, and we call that A. Call that angle theta. So in my picture, sine theta is B over C. Cos theta is A over C. Trig ratios. So what is sine squared theta plus cos squared theta? You square this, b squared over c squared plus a squared over c squared. Common denominator is c squared, b squared plus a squared. Looks nothing like 1, but you suddenly remember Pythagoras comes to the rescue. And Pythagoras' theorem says that a squared plus b squared, the square on the other sides, sum of them is equal to that. Yo. And it's equal to 1. So we've just proved that sine squared plus cos squared theta equals to 1. You can forget your own name. Please don't forget the strict identity. And then you have other very interesting formulae. I mean, these are so cool. They give you goosebumps on goosebumps. Compound angles. Sine of a plus b. You can expand that out. Sine of a minus b can be expanded. And similarly with cos of a plus b and cos of a minus b. And these will give rise to very interesting and new formulae. But before I go there, we had the other identity, and that is 1 plus tan squared theta is sec squared theta. When you're asked to prove an identity, always write everything in terms of sine and cos. So if you look at the left-hand side here, the left-hand side is 1 plus tan squared theta. What is 1 plus tan squared? Break it down. Tan squared is the same as sine squared over cos squared theta. This is 1 over 1, so take the common denominator is cos squared theta. 1 goes into cos squared theta, cos squared theta. Cos squared goes there 1 time, so you get sine squared. So you got cos squared theta plus sine squared theta over cos squared theta. But we just proved that cos squared plus sine squared is 1. So 1 over cos squared theta is, sec squared theta. And there we've just proved the identity. It's pretty straightforward, but the trick is to write everything in terms of sine and cos, and you'll be on your way. There's a formula that I would like to prove very quickly. We know that sine of a plus b, I'm not sure whether you did this in school, but you can show that sine of a plus b is sine a, okay, cos b plus cos a sine b. So now we look at something called the compound angle or double angle formula, sine of 2 theta. What is that? Well, sine of 2 theta is nothing more than theta plus theta. So if I compare what I've written here, theta plus theta, so theta is a and b is a theta. So if we expand that out, sine of a would be sine of theta, cos of b would be cos of theta, because b is theta. Cos of a, cos of theta, sine of b, sine of theta. Whoa, look at this. They're identical. So this is 2 sine theta, cos theta. So I've proved a very, very important and useful trig identity. Sine of 2 theta, the double angle, is 2 sine theta, cos theta. As a challenge, I would like for you to prove or obtain an identity for cos 2 theta. If you get that, that means you're cool with trig identities. All right. Okay, so we're really required to prove this trig identity. So if you look at an identity and you recall, an identity is true for all values of theta in this case. So when I look at identities, I look at the left-hand side and look at the right-hand side. And I like to work on, obviously, the more complicated side. I mean, it's pretty obvious that you can't prove 1 equals to the left-hand side, but it's easier to go left-hand side, simplify that, and then we hopefully get the answer to be 1. So the proof itself shouldn't be too difficult. So the proof is going to be the other. So we are required to prove tan squared theta times cos squared theta plus sine squared theta all over tan squared theta equals to 1. Now there's several ways of doing this, Well, what I like to do is, whenever I see a tan, I like to write that as sine over cos. So it tells me that tan squared would be sine theta over cos theta all squared. That is tan squared theta. There's my cos squared theta plus sine squared theta. Tan again was sine theta over cos theta squared. Now, there's no unique way of actually proving trig identities. I mean, there are elegant ways, there are shorter methods, but this is what appeals to me when I look at this question. So this is going to equal 2, so we're going to have sine squared theta over cos squared theta times cos squared theta plus sine squared theta. I'm just going to do this slowly because I'm just demonstrating how this works. What is going to be equal to? Well, what's going to happen here? This you can see straight away. Something beautiful happens. The cos squared will cancel out. And what you're left with then is just sine squared theta, which is that sine squared theta. And here I'm just going to take one more step. That becomes plus sine squared theta, which is this guy on the top. And now you're dividing by a fraction, and you know this as early as grade 7 or 6. You invert that fraction and you multiply, so you get cos squared theta all over sine squared theta. And my, you look at this and say, brilliant, that cancels with that. And what have we got? We got this sine squared theta, and we got a cos squared theta. And we will remember from our early studies of the fundamental trig identities that cos squared theta plus sine squared theta is equal to 1, which is exactly what we wanted to prove, and that is quite easily done. Brilliant. So we presented with another identity to prove tan squared theta minus sine squared theta is equal to sine squared times tan squared theta. Now here's the thing, you can either start off proving the left hand side equals the right hand side, or the right hand side equal to the left hand side, not simultaneously, because when you start transferring things, no, it doesn't work. So you've got to choose a side to work with. So in this case, I'm going to choose the left hand side. I'm going to simplify that, and hopefully I can show that it's identical to the right hand side. So when you look at the proving identities, do not mix left and right. Keep them separate. Choose to work with either the left hand side or the right hand side. So here I go. I am choosing the left hand side, which is tan squared theta minus sine squared theta. And I told you I'd like to write tan squared always as, well, in this case it will be sine squared theta over cos squared theta minus sine squared theta, like this. You can put this over 1 if you wanted. And what you can do, and I can see that sine squared theta is common. There's my sine squared there too. I just keep one eye on the right hand side and see how things progress. So if I take a sine squared out, I've got something like 1 over cos squared theta minus 1. And so we have 1 over cos squared theta minus 1, and that's going to be sine squared theta. In fact, if you wanted to, you can even take a common denominator there. There's an easier way, but if you take a common denominator with what happens in the brackets, you have 1. This is 1 over 1, so 1 goes there. You get cos squared, so you have 1 minus cos squared theta like this. And you're thinking, my goodness, what is this? It looks so much more complicated. Not really, because that's sine squared theta. That's the sine squared. 1 minus cos squared theta, by the way, is nothing more than sine squared theta over cos squared theta. And have a look at this. What is sine squared over cos squared? It's tan squared theta, which is now equals to the right hand side. Whoa, done. QED, quite easily done. Amazing, beautiful. Let's just come back to the one here. What happened here? 1 minus cos squared. How did that become sine squared? Let me write this as what I would like to call a little aside. Remember the fundamental? Sine squared theta plus cos squared theta always equals to 1. So sine squared theta is 1 minus cos squared theta. There we go. 1 minus cos squared theta is sine squared theta. And that proves the identity. Simple, straightforward. Do not rush. Write neatly. Okay? And apply the fundamentals, like for instance the definition of tan in terms of sine and cos. Take a common denominator. Bang! Thing works out beautifully. Yeah. So I would say up to this point, I think we're pretty clear. You know, you've got to keep doing problems, and the more problems you do in trig identities, as also involving special angles, the easier it becomes for you. So I'm just going to say for now, that's all for now, because the next lesson we'll be looking at periodic functions and graphs of trig functions. So thank you very much.